So this one is an exercise which is related to the astrophysics and cosmology. And in the first question, in the 18th century, the Herschel discovered an irregular shaped galaxy. This galaxy now known as NGC 6052. As in shown in the photograph, you can see light from NGC 6052 has a redshift which is equals to 0.0158, which if a galaxy is giving a redshift, it means the wavelength is increasing or it is moving away from us. So the first question, what is the meaning of a redshift? Redshift is a like change in or increase in the free wavelength as the source is moving away from the observer. So the term redshift always refers to the increase in the wavelength when the object move away from the observer. So, or the source is moving away from the observer. Calculate the distance of this galaxy from Earth. The h naught, the Hubble constant, is given to us. So how we can work out the distance? According to Hubble's law, the speed at which these galaxies are moving is equals to h naught, the Hubble constant, time the distance between the observer and the source. So if the galaxy is far from us, it will move faster as compared to galaxy closer to us. So we need this d. So it will be v divided by h naught is equals to d. So h naught is already given the Hubble constant, but what about the v? How we can work out the v? We can use a redshift. As the redshift is given in the question, the z, the redshift is equal to 0.0158. So the redshift, which is 0.0158, so the redshift, which is denoted by z, is equal to v divided by c. What is the v? V is the speed at which the galaxy is moving, and c is the speed of the light. So if we have the redshift, which is 0.0158, speed of the galaxy we don't know, and the speed of the light is 3 into 10 power 8. This is divided, other side will be multiplied. So this will give us the speed of the galaxy, which is 4.74 into 10 power 6 meter per second. That's the speed of the galaxy. So we have the speed of the galaxy and we have Hubble's constant. So we can work out the distance. So 4.74 into 10 power 6. The speed and the Hubble constant is 1.62 into 10 power minus 18 second. So this will give us this distance, which is 2.93 into 10 power 24 meter. The next part, the recent photograph of the Hubble Space Telescope shows that NGC 6052 actually consists of two galaxies that are colliding. So if you can see that in the 18th century, the irregular shape, what it appeared actually, it was like a collision of the two galaxies, like more clear image. The galaxies are accelerating towards each other. Explain why the acceleration increases as the time passes. So what will be the reason for that? Because the gravitational force, when the objects are closer to each other, the gravitational force is stronger, and it follows the inverse square law. When the distance decreases by 2, the force will increase by factor 4. If a distance decreases by 3, force will increase by factor 9. So what actually happens, as the galaxies will come closer to each other, the gravitational field strength will increase. So as it follow the inverse square law, so the acceleration of the galaxies will also increase as the force is increasing. Then in question 2, the Hertzsprung and Russell diagram shows a relation between the luminosity, like how much power is there, and the surface temperature. So this is for a main sequence star, a cluster of young stars. So as you can see, if the temperature, this Remember one thing, the Hertzsprung-Russell diagram is always for decreasing temperature. Here we have a low temperature and here we have high temperature. So the objects, the stars which are having a high temperature, they have high luminosity. Low temperature, they have low luminosity. Mark on the diagram the position of a star similar to that of sun. So the sun will be here, like similar to that of sun. So it will be in this region. Then the appearance of the HR diagram changes as the star cluster evolve. Explain the change in appearance for the HR diagram as a star cluster get older. So it is actually related to like the star cycle. What actually happened? Like first, when there's a hydrogen, when the hydrogen, like these all stars are main sequence stars. These are the main sequence stars. Then what will happen as the hydrogen fusion ends? The star will evolve into a red giant. And basically, when the hydrogen fusion ends, the radiation pressure reduces for the star size decreases and it started the hydrogen helium fusion. As a result, the size of a star will increase, more energy it will give out, even though temperature might not be, temperature will be high as well as the luminosity will be high, so it will be a red giant. So from main sequence, it will turn into a red giant. Then what will happen? When a helium fusion ends, the red giant will evolve into a white dwarf. And what are white dwarfs? White dwarfs are basically the stars which are having a high temperature, but because the size is small, so which region we'll find these white dwarfs? We'll find in this region. So in this region, we'll have a red giants here, and then we'll have a white dwarf. They have a high temperature, but they have low luminosity because the size is small. And the comparison between the red giants, the red giant relatively they have like size is big, large size, but the temperature is relatively small, the surface temperature. But for white dwarf, their size is small and the temperature is very high. So you just have to mention like how the star will evolve and using those points. So when you mention hydrogen fusion ends, you will score 1 mark. Then the helium, then it will not be in the main sequence, it will be above the main sequence star. And then it will turn into a red giant. Red giant, as the helium fusion star turned into a red giant, and it will be above the main sequence. When helium fusion finished, it moved to white dwarf, and its temperature will be low. Temperature will be high, but the size will be small. As a result, it will have a low luminosity compared to that of red giants. Then 100 years ago, the Andromeda galaxy was thought to be a group of stars within our galaxy. In 1923, the Edwin Hubble made observation on the standard candle. It's like standard candle, we assume that the objects have a known luminosity and the flux changes with the distance. If they're closer, give a high flux as compared to as they're away. So he concluded from this observation that the Andromeda must be outside of our galaxy. The graph shows a part of a spectrum of radiation received from this galaxy, the relative intensity and the wavelength. The two intensity minima represent the line in absorption of a spectra of calcium. And in the lab, the two lines have a wavelength of 394 nanometer and 396 nanometer. Determine the velocity. So how we can determine the velocity? Basically, we'll work out the redshift first. So the change in the wavelengths, like 393 and 396 are there, but these are the in the lab, these two lines are 393.4. So what is this line? because here 10 box 1 2 3 4 5 6 7 8 9 10 10 boxes, so each is representing like 0.5. So 390.5, 391, 392, this will be 393, and this is 393.4. Like what we receive from the galaxy is 393, but what we observe in the lab is 393.4. That, so this, we work out the change. Either we can take a lower limit or the upper limit, it does not make difference. So first we'll work out the redshift, which is change in wavelength divided by original wavelength. So what is the change? So 393.4 minus 393 divided by original wavelength 393.4. That will give us the redshift. And after getting a redshift, the formula, the redshift is equals to speed of the galaxy divided by speed of the light. So this will multiply. So Z will be equal, Z into C will give us the speed of the galaxy. So this will be like 0.4 divided by, the redshift is 0.4 divided by 393.4. So this will be 0.4 divided by 393.4 times the speed of the light, which is 3 into 10 to the power 8. And this will give us the speed of this galaxy, which is 3.05 into 10 to the power 5 meter per second. That's the speed of this galaxy. You can also take this value and then compare with this one. Then the original, like this is 396.5. So 396.5, this one, and this 396.9. So you can say 396.5 minus 396.9 divided by 396.9. So you will get the same answer. It won't make difference. The dust in a space around the star may affect how bright the star appears to be. It claimed that the dust around the standard candle would lead to a conclusion that standard candle is having a greater distance from the Earth than actual. Assess this validity of this claim. Basically, in a standard candle, what we say luminosity is the radiation flux is equals to luminosity divided by the distance, which is 4 pi d square d. So the flux vary with the inversely proportional to the distance. So what happened if, like, there was a star and that star is surrounded by the dust, so we'll receive less radiation as compared to a star which is not having the dust. So as we reduce, like, less flux we'll receive. If the flux is divided, the distance will increase, means that star will appear that it is far from us. So radiation flux is luminosity divided by 4 pi d square. And if the flux decreases, it means the distance will increase. So the star will appear far from us as we receive less flux from the star due to the presence of the dust around it. So these are first two questions from the exercise, Astrophysics and Cosmology. Next session, we'll do more from this.